All right, well, we got part 2 going on here. So here on 25, if it takes 78.2 joules to raise the temperature 45.6 grams of lead, calculate the specific heat and the molar heat. So again, what equation do we need to use? Q equals MCAT. Okay, so what am I looking for in this one? C. So do just a little manipulation. It's going to be M times delta T divided by Q. Now you can just plug in here and then solve for it.
It's Q divided by M
God dog it. I used to be pretty good at all this stuff. I really believe the bread's beginning to mold. Golly. C is equal to Q over M delta T. Just keep keeping me honest, okay? Can I start the video over again and just act like I didn't make that mistake? All right, I'll trim that out. So, C is equal to Q over M delta T. So we know what's Q equal to? 78.26.
2 joules.
2 joules. The mass is equal to 45.6 grams. And the change in temperature? 13.3. So very simple problem if you, as long as you know how to recognize this and see this. This equation, I think it's given in this form on the AP test in terms of specific heat versus in terms of Q. But all of this turns out to equal. Anyone, you all have it. Don't trust my answers. My answers have been wrong all day. 0.129 joules per gram degrees Celsius. Okay? Now, how do I change that to molar heat capacity? Multiply by the molar mass of lead, which is 207.2.
Yes.
And that all turns out then to equal
26.7.
26.7. And grams cancel, so it's joules per mole degrees Celsius. All right? Pretty straightforward problems. Just got to know the difference between when you're mixing two things, hot things, versus just dealing with one thing. You should always be able to convert between joules, kilojoules, grams, and moles, which are just things that we've been doing all year long anyway. All right, so that has all been under the guise of potential and kinetic energy. How do things absorb energy? How do we measure the amount of energy that they're absorbing and all of those things? So now we really want to start getting into energy itself. How can energy be transferred and how can energy actually be measured? So, if I am correct, you should have finished with 1C, and then we did, everything was kinetic and potential energy. We ended up under potential energy on that, okay? So we're gonna go D. Is this still on the video? Am I too far left, or can you still see on the?
Yeah,
I can see it. You're in.
Okay.
You're good.
All right, well, I've zoomed in and only using this half of the board, so hopefully it'll be more clear, bigger, easier to see. Trying to figure out ways to make things better. All right, so energy. Energy can be transferred in two ways. Or really, transfer between things in two ways. Transfer in two ways, which is going to be either work or heat. So delta E is always going to be Q plus W, where Q equals heat, W equals work. Now, I may not be in the screen on that one. All right. So, the first way is by doing work. Does anybody remember from physics or from 8th grade physical science how you calculate work, what work equals, or any of that?
Isn't it the path integral of the force?
Well, that's a little more complicated than what we need. Just in non-calculus based physics, what would the equation be?
Force times distance.
Thank you very much. Force times distance. So work is equal to force times distance. When gas molecules expand, they do work on the surroundings. Okay? By applying a force against the weight of the atmosphere. So if we feel this can right here, it's kind of cool, right? But it's not like super cold or anything. Feel the can. Okay, it's just room temperature, but it feels a little cool, but nothing big, okay? So now I'm gonna go, this is an air cleaner. So the gas is now expanding. As I spray this, and I spray off, and just try and clean a little bit, spray that salt down into the sink, okay? So as I'm doing all this, so now feel the bottom of the can. What's the big eyes mean?
It's really, really cold.
Okay? It's really, really cold. Didn't put it into a fridge. Yeah, I don't want to discriminate against y'all right here. Okay? If you feel the top of the can is what it felt like before. Okay? Because we're down to about this much left in the can. Why did that happen? Why did it get cold? Go ahead, Zane.
For the gas molecules to expand, they needed energy, so they took an energy from the surrounding, and we perceive that as cold.
Okay, they took energy from the surroundings, which is the other, the liquefied air or whatever's in that can, the can itself, and then we put our hand on it. All that energy is being used to allow the gas molecules to expand. They're doing work. Work is a form of energy. Okay? James Prescott Joule figured out that heat and work were related to one another. Heat is used to be measured in calories. And so what he did though is, can you see me over here?
No.
All right, we'll go here. He took a bucket of water, which he knew the exact amount of water was in. In that water, he put a paddle. And then around that paddle, he wrapped a string, which then went over a pulley to where he attached a mast to it. Okay? Now, 8th grade math, 8th grade physical science, if you've taken physics, you can know the potential energy. If we know that this is 1 kilogram or however much it happens to be, using the formula mgh, we can get the mass times acceleration of gravity times the height above the ground. We can get the potential energy that's in this. And so if we let that fall, then we know how much energy is being released as it goes all the way down. Well, the temperature of the water here went up. As this falls, it spins the paddles, and as the paddles spun, the water warmed up. And so he was able to figure out, okay, so this is the energy in joules, this is the heat in calories, and that's where we come up with the 1 calorie is equal to 4.184 joules. It's the mechanical equivalent of heat. It's how much heat and work are related to one another. Now we always calculate everything in terms of joules now, but it's the same. So work measured in joules is the same kind of as heat. They're very related. And so that's why we can put them into the same quantity here. Okay? So this, by the way, is oh my information. You will not be tested on this. This is just kind of how he came up with it. I think it's kind of interesting and ingenious way of measuring how much energy and heat, how they're related. Okay? So, work is also done to break bonds in a chemical reaction. So that's one way in which energy is going to be transferred. We're not going to really focus on this. When you get into more complicated, when you kind of get into classes like thermodynamics in college, they're going to combine the physics and the chemistry together along with a lot of calculus. It's a very difficult class. Talk more about the work aspect of a chemical reaction, but we're really just going to focus on by the heat, as heat. That's how it can be transferred, as work, by doing work, or as heat, which we're going to call thermal energy. Thermal energy. Now, this is where we're going to define heat. Heat is defined as the energy which flows from a hotter object to a colder object. And what determines how hot or cold something? How do we measure, how do we tell which one's hotter, which one's colder? Very simply. How do you know if something's hotter or colder?
You touch it.
You touch it, okay? That means it's hotter or colder to you, okay? How can we measure, what's just a measure of hotter or coldness, hotness or coldness? The degree, temperature, okay? Obviously the hotter thing is the higher temperature, the colder thing is the lower temperature, but temperature is very relative. I put a piece of ice into my hand is hot in comparison to the ice. It's the higher temperature. But if I take that same hand and put it onto a skillet on the stove, now that's not, it's not very smart, but my hand is now cold compared to that skillet. So it's all relative, hot to cold. Now, let's just say that it's a snowy day. We always want to have another snow day, another day to get out. Yeah. And we go and we see it snowing, we go and we put our hands onto the window. And our hands feel cold. And the question is why? Is heat leaving our hand going into the window, cold leaving the window coming into our hand, or both happening at the same time? Wish y'all could see on the video the wheels just churning in their brains, trying to figure this one out. What do you think?
Heat leaving our hand going into the window.
Heat leaving our hand and going into the window. There is no such thing as cold. If I want to make this room totally dark, what can I do? Can I turn on a dark switch? You just gotta take all the light out, right? And so to take all the light out, I can make it dark. So darkness is simply the absence of light. Okay? So if you're in the dark, that just means that there is no light around you. That could really preach pretty good, but I'm not gonna go there. But in order to make something cold, then, we don't add cold to it. Like right now the air conditioner's on. It's not really putting cold air in, it's taking the hot air out. And so right now in this, we have the return air vent right over here. So it's sucking the air, the hot air, out of the room. And it's taking it to just past on the other side of the wall of that closet. There's an air conditioner unit that has cold water running through tubes. So the hot air is passed over those cold tubes, and the heat transfers into those cold tubes, and the air comes out on the other side with less heat in it. It's colder, and so as a result, they blow that back in. The reality is it's the same air, they just extracted the heat from it. A refrigerator is going to work the same way, except it uses Freon, or the air conditioner in your car uses Freon. And so the Freon is under pressure. The compressor, you hear that thing kick on in your car, you hear it kick on in the refrigerator. The compressor compresses the Freon and changes it into a liquid. And then they pump it through, and then it goes through what's called an expansion valve, which then allows the pressure to be released. And when you release the pressure, it allows it to turn back into a gas. Just like if you have a Bic lighter, or even one of this lighter right here, it's a liquid inside of here, but when you open it up, okay, when you open it up like this and just take the pressure off, that liquid is turning into a gas, and a gas escapes, okay? So the Freon is compressed. When it takes the pressure off, it's allowed to evaporate, and just like this, when it evaporates, it's doing work, so it's getting cold, it's taking energy to break the bonds. It gets very cold, so then the hot air from your car, the hot air from the refrigerator, is passed over those cold coils, and then the cooler air is put back in, and the hotter air is behind the refrigerator. It's always hot behind the refrigerator because the heat's being extracted from it, okay? Plus the energy of the compressor. So heat is defined as the energy which flows from hotter to colder, but temperature is what determines the direction of heat flow. It always flows from hot to cold, okay? Temperature determines the direction of heat flow. So B, temperature determines the direction of heat flow. Always flows from hot to cold. And hot being higher temperature, cold being lower temperature. So if you want to cool something off, you always have to have what we call a heat sink. You have to have something that's lower in temperature than what you're trying to cool off, so the heat has something to flow into. But it's because of this that absolute zero is impossible to reach. Because in order to get to absolute zero, you'd have to have something colder than absolute zero. But if absolute zero is as cold as you can get, there's no heat sink that the energy can get into to get to absolute zero. Now they've gotten to within like millions of a degree or something, but it's impossible to actually get to absolute zero because it's always going to flow from hot to cold. So, now I said that energy can be transferred in two ways, heat and work. Heat can be transferred in three ways. So in other words, there is a difference between total internal energy and heat. Because energy is the work and the heat combined. It's the way you can transfer it two different ways, but heat can be transferred in three ways. Do we know what these three ways are? when you put a pot on the stove, I have a pot at the house and we put it on the stove and it's got the all metal handle, and you boil it in water or whatever, and you go and you grab the handle, and the handle is super hot. Now the handle has not touched the stove. This is a gas stove. It hadn't touched the fire. Why did it get hot?
Is it conduction?
It is conduction. So what does conduction mean?
The heat like flows in the object.
Okay. So what has to be true about conduction? It's heat. Will the heat be conducted if I take the pot off the stove? So what does it have to be doing? So what would be a definition of conduction, I guess is what I'm looking for.
The tendency of an object to reach a uniform heat throughout.
That's more of like an equilibrium thing. It's heat transfer by direct contact. You put the pot on the stove. You put the pot on the stove, the part that's on the bottom, the metal part, absorbs the energy. Those molecules begin moving faster and faster and faster. Well, because they're touching other molecules, they bump into those and it transfers that heat and they start moving faster and faster. Eventually, all of the molecules of the pot, because they're all touching in one way or another, they all start vibrating faster, and then that heat starts going all the way down that handle, and the molecules are all moving very fast, and we could say it's very, very hot. But it's by direct contact, they're touching one another. Okay? What's another way? You guys have heard these before. This is not new. What's a modern type of oven called? A convection oven. What makes it different from a normal, what we call a conventional oven? It uses air. In a normal oven, you have the heating element, the piece of metal in the bottom that gets red hot. And you usually have one on the top too, so you can broil. So the heat is right there on the inside. But in a convection oven, what's different? That's right, the heating element's not in the oven. You heat it on the outside and then use a fan and blow the heat in. So convection is when you physically move a heated object from one place to another. Heat transfer by physically moving the heated object from one place to another. So when we're talking about this air conditioner system in here, we are going to use convection to physically move the air, the hot air, the heated air through the vent to the air conditioner on the other side of the wall. But then that air passes over those cold coils and touches them, and that heat is transferred then to those cold coils via conduction. And so then the air gets colder, and as it passes through, then it comes in here. Now that water that's going through there now eventually gets warm. So they have to, again, by convection, pump it all the way to where behind the gym and the cafeteria over in that corner, by the practice football fields and stuff, they have those big chillers. And so they're going to then let that water then get recooled and pumped back. And so that's all convection, physically moving the heated object from one place to another. So the heat from this room eventually ends up over here. Well, I'm pointing the wrong way. I always point the wrong way. The gym is somewhere back that way, isn't it? Okay, it's just out there somewhere. Okay, I just point randomly wherever it is. I really have a horrible sense of direction, and it's just, I'm used to try to, act like I didn't, I've just given into it. All right, I call myself direction lexic, and where I think that if I need to go left, I ought to go right, I'm always opposite. So, I let my wife tell me how to get to places and without being offended. All right, so what's the third way? How does the heat get to us from the sun? Photons traveling in waves, which is a form of electromagnetic radiation. Heat transfer via waves. Okay? So your car has a radiator, right? Everybody knows that you have a radiator, it's got to have the water and the antifreeze in it, okay? But the radiator is always made out of some metal, usually aluminum, and it's got a bunch of fins on it. And those fins have a lot of surface area. So when that hot water from your engine is going through there, it's transferring the heat by conduction to that metal in the radiator. But then the radiator then has the fan blowing on it, helps it to radiate that heat out to the surroundings, to the atmosphere. You want to have a certain, a lot of surface area so it radiates it quickly. There's a lot of places for the heat to escape. You may have seen in an old house a radiator, kind of looks like an accordion. It's usually against the wall. You run hot water through that, and then the whole metal thing gets warm, gets hot, and then it radiates the heat to the rest of the room via waves. The same thing on your fireplace at your house, whether it's gas or wood, it's going to have the fire there, but the heat's going to radiate by waves into the room. Okay, and by the way, the waves are always infrared, is what you see. I was actually watching Cobra Kai. No, it wasn't Cobra Kai. I was watching an old show called Las Vegas. Anyway, they were using an infrared scanner to see how many people were inside the building. Now it made it a little bit too obvious, but you can pick up the heat traces rather than the actual visual. So you can follow the infrared rays, because that's how heat's being conducted via waves, infrared. Okay, so these are the three ways in which heat can be transferred. So energy can be transferred, but via work. You can either do work or as heat. Heat can be transferred in these three ways: conduction, convection, and radiation. All right, one last concept. And then we are done until Friday. Well, not really, but I won't see you again until Friday. That was all D, right? So this is E. Internal energy. This is the sum of all kinetic and potential energy in a substance. If I take this piece of paper, there is no way for me to measure how much potential and kinetic energy there is in this paper. The electrons, we don't know exactly where they are. The electron repulsions are constantly changing, as things move. Okay, there's a certain amount of potential energy based upon what atoms are bonded to one another in the paper itself. And so there are too many variables. There's no way to measure the total internal energy of this. But if I take it and I burn it, now there's a whole lot of heat being given off. Now, I don't know what the potential energy, the internal energy is of the ashes that are being produced, of the gas that's being produced. I cannot measure the internal energy of that. But what I can measure is how much heat is released when the paper changes into ash. If I have this in an enclosed container to where I can keep the heat in an insulated container, then I can measure how much heat was released. And we can do that. Okay, let me just say this. It's impossible to know the internal energy of a substance. Too many variables. But changes in potential energy can be measured. Okay, so changes in potential energy is how we measure. And this is where we could use what's called a bomb calorimeter. That went off.
Why is it called a bomb calorimeter?
That's a great question. Okay. This is called the bomb, is the reaction vessel. Okay, this is where the reaction is going to take place. And they're not going to explode anything, but they are going to burn it. So when you say Snickers has 280 calories in it, the way that they measure that is they take the Snickers, they dehydrate it, get all the water out of it, and then they put it into here and hook it up to electricity where they're going to actually burn, they're going to ignite it and burn this. Well, that's going to make this whole chamber get hot. Now they have this calorimeter, this perfectly, well, nearly perfectly insulated container that has a set amount of water in it, and they can measure how much the temperature of the water goes up. Now again, a calorimeter like this is going to constantly be the same mass. You put the same amount of water into it, so we could use the heat capacity of the heat calorimeter and not have to measure the mass of the water in the calorimeter every time. We just have the calorimeter constant. But you burn this. We don't know how much energy is in the Snickers. We don't know how much energy is in the CO2 and the water and all the ash that is given off. But we can measure how much heat is released when that Snicker bar burns. And so that heat is released into the water. It stirs it so all of the water gets heated evenly, because if you get hot spots, then you're not getting an accurate reading of how many calories are being given off. And so we just measure the change in temperature, and we measure how many calories or joules are released when that Snickers burns. All food is done this way. It's measured in a calorimeter. Okay? But we know that a food calorie is actually a kilocalorie. 1,000 calories, a nutritional calorie. And on your food labels, from what I've read in the past, I'm not 100% sure on this, but I'm pretty sure that that they only have to be plus or minus 20% as far as accuracy on how many calories and the different things. So a Snickers bar, I'm gonna do the math easier, if it's 300 calories, that means it could be anywhere from 240 to 360. You know, so it's just got that range, I mean, as far as how accurate they need to be according to FDA guidelines. But we can measure the changes in that energy, how much heat is released, okay? Using a bomb calorimeter. So they just call this reaction vessel because you're burning it, it's called the bomb. No explosions. And those things, I mean, they're only about this big. Okay, it's not very big. All right? So that's all about energy. Woohoo! Okay? It's all about energy. All right, well, that's going to do it for today. Tomorrow, I'm not sure exactly. I'll probably just have you do just a couple of more practice problems with specific heat, and kind of go from there. Not a whole lot, probably only like 2 or 3 problems, just to kind of make sure that you can do those. And then Thursday, we're going to start in on enthalpy, which is the measure of the heat at constant pressure. So it's going to be just the Q part of the Q plus W. And that's what really we need to learn how to do. And there's going to be 4 or 5 different ways in which we can measure the heat of a reaction, the enthalpy of a reaction. And that's what we're going to learn how to do for the rest of this. Now, we also, just so you know, we're doing chapters 5 and 19 in the textbook together. And so if by chance you wanted to actually like read the textbook to kind of keep up with this, you're more than welcome to do that as well.